Hello. First of all, I'm Matt Vaughn. I'm from Embry-Riddle Aeronautical University. For my project here, I coded up a vorticity model based off of Dr. Wayne Schubert's vorticity model that he made back in 1993 in Fortran. What's novel about this model is that it is in MATLAB, a little bit of an easier language to understand for people just getting involved in programming. It also has very capable matrix manipulation techniques in it, which made it ideal for all of the heavy computing that we were doing in this experiment. Basically, what we did was that we took a strip of higher vorticity air here and time integrated it over a domain to simulate the tropics, and saw how this strip of vorticity, this strip of spinning air, evolved over time. And we noticed that the dimensions of the strip are very important as to how the strip evolves over time. You can see in these three cases that the ratios between the length and the width of the strip are all the same, but just at a bigger dimension. So you can see over here that we had case 1 as 1,350 kilometers by 150 kilometers, case 2 a little bit bigger, and case 3 a little bit bigger than that, but all the same ratio. But as you go down along the line, integrating with time, you can see that they evolve into different vorticity fields, either merging into one vortex, or kind of a hybrid stage in the process of merging, or they could evolve into two separate vortices. Now the point of this is to better model the tropics, and especially the vorticity associated with the intertropical convergence zone, that band of higher vorticity air around the equator. And hopefully with this research and more like it, we could try and understand how these strips evolve when they break off of the ITCZ, and that could help us with our tropical cyclone forecasts, and especially how whether they would form and strengthen in their current state that we observe them.
Okay. So what did you learn about this project, about other things you want to research? Did you enjoy doing this project and all the modeling? Do you want to continue that, do more modeling, less modeling?
At first, I really didn't think I would like modeling at all, but after coding this model and kind of getting to call it my own, coding up my own model, it really appeals to me that you can simulate our atmosphere with something that is now, in retrospect, a fairly simple model. Very few lines of code, probably less than 100 or 150 lines of code, to write this entire thing in MATLAB. That is just really interesting to me, that we could simulate our atmosphere like that.
Did you write the entire code from scratch on your own, or did you copy and paste from like websites that already had some things pre-written?
Myself and Dr. Gwynn worked collaboratively on this, but we both made this code from scratch in MATLAB. However, we did use Wayne Schubert's model as an example.
Okay. And what was your motivation for doing this project? How did you come up with the idea to model Wayne Schubert's vorticity model?
Well, my research advisor for the experiment, Dr. Gwynn, his graduate advisor was Wayne Schubert, and he did a little bit of work with these vorticity fields, especially with a long infinite continuous strip back in graduate school. But he wanted to see what these finite strips would look like, where it's not infinite across the domain, but has set dimensions. And he enlisted me to help him with it because of my programming experience that I accrued over my undergraduate years.
Okay. And what was the initial process? How did you first get started? Just coming up with the idea and the plan about how you're going to go about approaching this research project?
Dr. Gwynn explained the general goal of the experiment, and then we immediately launched into the mathematics behind it, which, this being a pseudo-spectral model, I needed to learn Fourier transforms, which is a type of mathematics that I didn't receive in my standard calculus courses. So that was the first part of this project, was just understanding the mechanics behind the models, as well as the dynamic equations going along with it. And then we got more into the programming aspect and figuring out what was the best method of time integration. That was another big find that we saw, was the standard time integration for this, the Runge-Kutta fourth order scheme, was very, very slow, really slow. and we managed to do very well with what's called an Adams-Bashforth third order scheme, which isn't as calculation intensive, but gave us the same results in the end. So we were able to use that scheme and get a lot more work done through that.
Okay. And for everyone that's not as well versed in meteorology terminology, can you explain what a pseudo-spectral model is?
Yes, a pseudo-spectral model, I kind of equate it to the matrix. You know, the red pill and the blue pill that Neo was offered. We kind of live in this physical space, an X and Y. But then when you take a function and you put it through a fast Fourier transform, you can convert it into terms of sine and cosine, which I call the matrix. It's now in this other world where you can describe the same function in sines and cosines. With the advantage of the pseudospectral model is that it made our math really easy inside the model. So we converted it into spectral coordinates, that's what they're called after they go through a Fourier transform, did the derivatives, and then basically took the red pill back into physical space and back into the real world to do the time integration again. And I found that just fascinating, how we could do that.
And do you plan on doing anything more with this project, expanding it a little bit more, or doing any more experiments, or with different, I guess, variables you're going to put in or take out?
Right now there aren't any plans to continue it, but I do find our beta plane work very interesting. You can easily see that the difference between the F-plane experiments and the beta plane experiments are huge. And that's because we added in the Coriolis force into the model, which is the effect of the Earth's rotation. Since these vorticity values are so low, the Earth's rotation has a huge effect on the way the vorticity element evolves. So I would be interested in trying to figure out what is really behind the results that we got in the beta plane experiment, if I could.